in quantum physics and mechanics, let's just call it kind of quantum technology as a placeholder, how much of what you teach and what you learn is theory and how much is generally accepted? Is there a percentage? Are we 99% theory and working to get 1% of the time accepted? Or
I think it's a good place to kind of start a conversation about it. So you mentioned quantum mechanics and mentioned the 30s. So around the end of the 1800s, around 1900 or so, people realized that, well, there were some claims that physics was done. Everyone solved all the physics problems except a few small mysteries. The small mysteries opened up into quantum mechanics writ large. You have this idea of chemistry going back to thinking about molecules and atoms. Ludwig von Boltzmann, founder of statistical mechanics, and he realized that there had to be quantized particles. People who do music often see quantization. You have different harmonics of an instrument, and these are all quantized based on the size of the instrument and the shape of the instrument. And so a lot of these things end up being quantized naturally. And so there's nothing theoretical about it in that sense. I think what has become new in the last 10, 20, 30 years even is the engineering side of quantum mechanics. It's really being able to take the fact that we understand how atoms and molecules and how these things connect to experiment, how these connect to theory, and how the theory connects back to experiment, all these things. Now, can we take those understandings and engineer something? Can we make something out of this? Can we then use these effects to do something interesting? So I think a lot of science starts off with quantifying something, understanding that something's wrong, realizing there's some problem here, then quantifying what's going on, checking your theory against what you predict it to be, improving your theory, and then coming with an experiment, new theory, an experiment, new theory, an experiment. So quantum mechanics is a very important interplay between what the theory says and what the experiment says, and that's actually how we validate the quantum mechanics. There's a theory that holds a lot of validity. The Nobel Prize last year was around violating inequality, that Einstein had put forth inequality, but Einstein put forth the idea that quantum mechanics was not correct. And so proving that it is correct has been a small cottage industry for many years that resulted in a Nobel Prize.
So Einstein, which is generally, at least from my perspective, held in high regard scientifically, he was wrong about quantum mechanics.
Yeah, profoundly wrong about quantum mechanics. It's really interesting because he did some very seminal works that really laid the foundation for the mathematics and the understanding of the quantum mechanics, and even won his Nobel Prize. But I think the Bohr-Einstein debates, he was on the losing side of that argument. That's all the arguments that he had with Bohr and Einstein. I mean, he said God doesn't play dice. I mean, probabilities at the heart of quantum mechanics, and in the way that I think about it, and the way that I try to explain quantum mechanics. So we start with probability first. And Einstein famously said God does not play dice, and this, I'm not sure if it's actually his quote, but it's often attributed to him. This is not the right way to think about quantum mechanics. And he had this EPR paradox, and again, was not the right way to think about quantum mechanics. So a lot of things that Einstein, I think, conceptually overlooked. I think his skill and ability as a physicist did not match his imagination as a philosopher.
Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.